Yeah. Hi, everyone. My name is Ida Ying, and I'm an incoming PhD student at Princeton University advised by Professor Zhang Liu. So I'm here today to present Zhuang and Kaiming's work on a decade battle on dataset bias. Are we there yet? So to talk about dataset in computer vision, we'll first start with MINIS dataset, historically a very important dataset from computer vision and machine learning. It is a digit dataset that consists of grayscale image from 0 to 9. All digits were originally written by humans and later resized to low resolution. So we have a famous scaling law saying that if we train on more data, we will improve model performance. So here, let's add more image and even more MINIS image. The limitation of this scaling in this way is pretty obvious. So the data is only from this very narrow MINIS distribution, and the model trained on them can only perform digital recognition, and it cannot do other computer vision tasks, or even the task on a different data distribution. So in other words, the way of scaling data is limited in the MINIS digit world, and we cannot expect the model to do any other vision recognition task. Ideally, we want a dataset to learn more general representation, not just for digit, and it naturally will require more diverse sets of image. Now, let's see an improvement to this. CFAR10. Unlike MINIS, CFAR10 includes natural RGB image. It consists of 60K color image across 10 categories from simple common objects like animals and cars. However, the images are still a low resolution, only 32 times 32 pixels. Now, ImageNet is really a leap forward in terms of data scale and quality. It pushed in the deep learning revolution we see since 2010. Its largest version has 14 million images and 21K categories, featuring everyday objects, animals, and things. Compared with previous dataset, it also contained more fine-grained classes, such as different dog breeds, musical instruments, and tools. However, here's another even larger vision dataset, YFCC 100 million. Just from the name itself, 100 million, you can see it's another magnitude larger than ImageNet. So it is collected from Flickr.com, which is a website of user-uploaded image. What's also different is that in this dataset, it does not have predefined categories like ImageNet. As a result, this limitation on what has to be in the image is now gone, and the resulting dataset is even more diverse in terms of coverage. It covers a wide range of content, travel photos, natural scenes, daily life, and human selfies. Different from ImageNet, which only focuses on label objects, YFCC reflects the real-world imagery, often contain multiple objects, or even no clear subject at all. In recent years, with the rise of image text pre-training and vision language models, dataset curated from the web with text description has gained popularity here. This kind of dataset don't have categories. They're collected from over the internet, not just from one website like YFCC. This results in a more diverse collection of web content, ranging from everyday life photos and product shots to memes and cartoons. And this is a very recent dataset called DataComp 1 billion. And we finally arrived at the billion scale. It is one of the largest datasets for image text pre-training. The example here reflects massive diversity, ranging from advertisement, infographics, instruction icons, and street scenes. Now, let's play a very simple game here. Here are 15 images randomly sampled from YFCC, CC, and DataComp. Can you identify which dataset each image comes from? I will wait for 15 seconds, so everyone can just take a guess. Yeah. So I don't know how you feel this task, but I think it's quite challenging, and we can hardly find any pattern to trace the image back to the dataset. So if all these datasets seem to cover so many concepts, and it is very hard to tell apart, it might seem reasonable to assume they are already general dataset, and they are all encompassing so that they might be just seen as an underlying word distribution for the image. Moreover, all these concepts we see in the real world also represent in these datasets. They seem quite accurately capture the entire world. So let's tentatively assume that this is true. Modern large vision datasets are already general enough. Well, in this work, we examined this view through a very simple but interesting experiment. Considering these three representative datasets, YFCC, CC, and DataComp. What we do in this work is extremely simple. We train a neural network classifier to predict which dataset each image comes from. This classifier is not tasked with traditional vision tasks, like classification or recognition, but on this seemingly artificial and contrived task of telling which dataset this image is from. This classifier is then tested on holdout validation image from these datasets that are not seen during training. Suppose our assumption is correct, this classifier should do no better job than random guessing, which is 33.3% accuracy on this task. So the baseline chance accuracy is just a random guessing. I would like to invite any audience just to guess what we actually got in this 3 dataset classification task. Please only take a guess if you don't read our paper. Yeah, you can just call out. 50-50. Okay, so I guess the accuracy is a bit lower, and it turns out to be the actual answer is 84.7%. So if we include more datasets, which the task will be more challenging, the model still reached nearly 70% accuracy, much higher than the chance level guess. This means these seemingly large-scale, general-purpose datasets still have their own idiosyncrasies, such that a standard neural network can easily tell them apart. In other words, these large-scale datasets are still incredibly biased. It's actually possible that this high accuracy can be achieved due to some very low-level artifact. For example, different datasets have different compression rate. They are less noticeable to humans, but can be easily exploited by neural networks. So here we add some corruption to the image, and we find that a model trained on this corrupted data can still achieve very high accuracy. In general, it's more than 70%. So what we did in this paper is not new. This classical paper named Unbiased Look at Dataset Bias by Torralba and Efros in 2011 proposed this dataset classification experiment. Back then, the dataset were quite specialized and small, and a human could easily tell the dataset source of image if they are familiar with these datasets. In their paper, an SVM classifier reached 37 accuracy for a 12-way classification task. Now, more than a decade later, we have much larger scale dataset, and they are supposedly much more diverse. But still, our revisit of this classification artificial task suggests our battle against dataset bias has not been won yet. So what is actually causing the classifier to be able to tell the difference? Well, we can first do some transformation, transform each image into some caption, which is more easily readable by human. We then perform the dataset classification task on the caption, not on the image. In this way, we still can achieve very good accuracy, about 63.8% for the caption classification. So in a follow-up work named Understanding Bias in Large-Scale Visual Datasets, we explore more transformation, such as transforming semantic segmentation, object bounding box, and image caption. We find the classification can still distinguish different datasets over 60% accuracy when transforming into different semantic representation. In other words, there are much bias in semantics. We're also prompting large language models to summarize each dataset characteristic by providing with caption. We can see YFCC are featured with outdoor, natural, and human-related scenes, and DataComp are about static object and digital graphics, and CC are just blend both of them elements. So suppose we see the dataset classification experiment as game, whereas neural network classifier try to be the discriminator and data curator are the generator, just like game. There is the equilibrium of game, which will have all really truly diverse datasets. But is this a realistic goal? Does it make sense to define word distribution for visual dataset? If so, how does it look like? Is it a random camera from a random location in the world, or something else? There's still a lot of questions in this pursuit of high-quality general vision datasets. And to summary, this work finds that modern large-scale vision datasets are still incredibly biased. Well, I actually have another slide on another work of us. We basically just try the classification on the LM output, and we still can surprisingly find that it can achieve very high accuracy, even on this very powerful frontier model using the same prompt there. In other words, these output from Rails to LM are also very different. And we even can find some very represented phrases from each LM. For example, GPT-4o use such as, and Cloud using to according to text, these kind of phrases. Yeah. So this is all I have for everyone, and thank you. I'm happy to take the question.
So, any questions? To your last point, doesn't that hinge on the fine-tuning of the LLMs rather than the datasets?
You mean this part?
Yeah.
Oh yeah, actually this part because I run out of time. For this part, we use the prompt to generate LM output, and then we fine-tune a text embedding model to classify which the generated response come from which LM.
I understand. I was just wondering whether it's more the data or more the RLHF, basically.
Well, we also try on base model, and it also can achieve very high accuracy, but less than 90% degree. It's about 80% here. So we basically believe it's about data, no matter it's the pre-training data or the post-training data.
Any more questions?
How much of it of this could be attributed to like the networks just memorizing images?
Well, I think it's a little bit different from memorized image because all these results we are not like evaluate all this reported accuracy are not evaluated on the training part they see during the classification. They are evaluated on the holdout part. Yeah, so it's more like a generalization behavior where you learn some general pattern about each data set, and then you can transfer to some unseen image sample from the same distribution.